Hello, welcome to this video example where we examine how to decide if a function is continuous, especially if it's a piecewise defined function. Here I have a piecewise defined function. F of x is either k times x if x is less than 1, or x squared plus 3 if x is greater than or equal to 1. What we'd like to do is to figure out what k should be, what that parameter or constant k should be, to make this function continuous. Notice that k times x is going to be a continuous function no matter what k is, and x squared plus 3 is a continuous function. The only place where f might not be continuous is where you switch from one definition to the other, namely at x equals 1. Let's see what happens there. Perhaps we'll start by graphing this function just to get an idea what it looks like. At x equals 1, we switch from having this k times x, which is going to be a line that goes through the origin with slope k. So I don't know, I'll maybe just draw a little bit of that there to get an idea what's going on. And at 1, we switch to this parabola x squared plus 3, a standard parabola shifted up 3. So if we have maybe 1, 2, 3, by the time we shift up, the parabola is actually moving up. It's going to start here and then continue up. That's kind of what the x squared plus 3 looks like. What we want to do is we want to take the line kx. Now if k, say, was 1, we would have a function that looked like this. Continuing on that way. And notice there's a big jump here. There'd be an open circle here and a closed circle there. We don't want that jump. We want those two curves to match up, to line up, to connect. So what could we make k to make that happen? Well, we have to make the slope big enough so the lines run into each other. Let's see how we could do that. What we want is to make the line look like that, essentially, so they match up. Well, to do that, we have to figure out what this point is right here. Notice, if we actually plugged in 1 to our function, f of 1 is equal to, well, we'd use the bottom definition. We'd use x squared plus 3. X squared would be 1 squared, plus 3 is 4. Okay, so the value of the function is 1. We need the line, the k times x, to hook up with that. So we need to, essentially, we need to make k times 1 equal to 4. So we better have k equal to 4. So if I make k equals 4, then this line has a slope of 4, go over 1, up 4. That's right, this hooks up now. So the only value that works in this case is k equals 4. Mathematically, what we're actually doing here is we're saying, what is the limit as x approaches 1 from the left of f of x? Well, given our definition, that limit is going to be k. And we need that k to be equal to the value of the function at 1. We need that to be equal to f of 1 if we want the function to be continuous. And that is, of course, as we said, 4. So k has to be 4 in this example. All right, well, maybe let's look at another example now and see if we can do a similar thing. How about this one? Now f of x is either x plus k quantity squared when x is negative, or k times e to the x when x is greater than or equal to 0. Why don't you spend a minute, pause the video, and see if you can solve for k to make this function continuous. The first thing you might notice is that the function k e to the x is just like e to the x, but it crosses the x-axis exactly at k. We might have something like that, and this value here is k. Initial value. Notice when x is 0, e to the 0 is 1, so we just get k there for f of x. Again, what we need to do is we need to make sure that the limit as x approaches the possibly bad spot, 0, just from the left of f of x, we want that to be equal to f of 0. This is one of the properties of continuous functions that we must satisfy. Well, what is this limit? This limit from the left uses the top definition here, uses this right there. So if we want to do that, well, we're taking the limit as x goes to 0 of x plus k squared, so that is going to be 0 plus k squared. And this has to be k. So we need a value of k that satisfies k squared equals k. When does k squared equal k? In other words, we have k squared minus k equals 0. So we also have k times k minus 1 equals 0. Well, that's true exactly if k equals 0 or if k equals 1. We should check that both of these will actually work. Let's see what happens if we make k equals 1. If we make k equals 1, then we're saying that we have x plus 1 squared and e to the x. Do those two functions hook up at 0? Well, e to the x goes through the point when x is 0 is 1. And when we look at x plus 1 squared, x plus 1 squared is a parabola, but it's just shifted over 1 to the left. So it would look something like this. Yeah, those look like they hook up. Everything's okay. It's okay that there's a corner there. We don't care about there being a corner as long as there's no jump in y values. What if k was 0? Well, if k was 0, then we would have just x squared, and we would have 0 times e to the x. That would be 0. This also works. This would look like half of a parabola and then a 0 function, where there's my axes, like that. So that also works. But these are the only two values. K has to be either 0 or 1 to make this function continuous. All right. Well, thanks for watching, and I hope this has helped.